Good morning, my dear students. In the previous lecture, we discussed the solution of the wave equation using the method of separation of variables. In this lecture, we are going to discuss the D'Alembert solution of the wave equation. We start by considering a one-dimensional wave equation, partial square u by partial t square equals c square times partial square u by partial x square. For x in the interval from 0 to L, and t is a positive. So we are also given initial conditions u of x 0 equal f of x, and partial u by partial t of x 0 equal g of x for x in 0 and L, and homogeneous Dirichlet boundary conditions u of 0t equal u of LT equals 0 for t bigger than 0. So our aim from this lecture is to derive the D'Alembert solution for this problem. Okay, in both this domain and also in infinite domain. So the basic idea in the D'Alembert solution is to transform the original problem to new axes where we can integrate the transformed equation easily. So the new axes are defined by xi equal x plus ct and eta equal x minus ct. Now we use the chain rule to express the first and second derivatives of u with respect to x and with respect to t in terms of the derivative of u with respect to the new variables xi and eta. So the first derivative of u with respect to x from the chain rule is just partial u by partial xi times partial xi by partial x plus partial u by partial eta times partial eta by partial x. From the formulas of the variables xi and eta, we see that partial xi by partial x is 1, and for partial eta by partial x is 1 also. So then we replace partial xi by partial x and partial eta by partial x by 1s, and then we obtain partial u by partial xi plus partial u by partial eta. Similarly, for partial u by partial t, it is partial u by partial xi times partial xi by partial t plus partial u by partial eta plus partial eta by partial t. Now, when we compute partial xi by partial t, we see that it's equal to c, and partial eta by partial t, it equals to negative c. Okay, so we end with this formula for partial u by partial t. Now we use the first derivatives, the formulas of the first derivatives to compute the formulas for the second derivatives of u with respect to x squared and with respect to t squared. So we know that the second derivative of u with respect to x squared is just partial by partial x of partial u by partial x. And as we did previously, we use the chain rule to compute this derivative. So instead of partial u by partial x, we substitute this derivative here, and instead of partial by partial x, we write partial by partial xi times partial xi by partial x plus partial by partial eta times partial eta by partial x, as we did previously. And then when we apply these derivatives here, we obtain that partial square u by partial xi square is the first term here. And then we have partial square u by partial xi partial eta, which is the second term here. From this side, we obtain partial square u by partial eta partial xi, which is the third term, and partial square u by partial eta square, which is the fourth term. Now we assume that the function u, I mean the second derivatives of the function u with respect to the new variables xi and eta are continuous. And that means these mixed derivatives are equal. Partial square u by partial xi partial eta equals partial square u by partial eta partial xi. So instead of partial square u by partial eta partial xi, we can write partial square u by partial square u by partial xi partial eta. So we end with this formula, partial square u by partial xi square, this term here, plus 2 partial square u by partial xi partial eta, okay, plus partial square u by partial eta square. In a similar way, we find that partial square u by partial t square equal to c square partial square u by partial xi square minus 2c square partial square u by partial xi partial eta plus c square partial square u by partial eta square. Now we substitute the second derivatives of u with respect to x and t in the wave equation, and when we simplify, we obtain this equation in the new variables, partial square u by partial xi partial eta equal 0. Now to obtain the function u, we have to integrate this differential equation twice, one time with respect to eta and one time with respect to xi. So if we integrate this equation with respect to eta, we obtain partial u by partial xi equal alpha of xi, where alpha any arbitrary function. Now we again integrate this function with respect to xi to obtain u, then u of xt equal the integration of alpha to xi, and then we add a function psi in eta, psi of eta. If we suppose that the integration of alpha of xi with respect to xi is a function phi of xi, then we obtain the solution is phi of x plus ct plus psi of x minus ct. Here, phi and psi are arbitrary functions. They are representing two traveling waves. Phi is a traveling wave to the left side, and psi is traveling to the right side. That means the solution u of x and t is expressed as a combination or a superposition of the two functions, the two waves, phi and psi, that are traveling in opposite directions. Our next task is to determine the functions phi and psi from the initial conditions. But before that, we noted that the partial derivative of phi with respect to t equal to c times the partial derivative of phi with respect to x, and the partial derivative of psi with respect to t equal to minus c times the partial derivative of psi with respect to x. We are going to use these two formulas later in this slide. So we start with the first initial condition u of x 0 equal f of x. So, but u of x and 0 equal 5x plus psi of x by substituting t equal 0 in the forms of phi and psi. So we obtain 5x plus psi of x equal f of x. This is the first equation, which is equation 5. Now for the second initial condition is on the derivative of u with respect to t. So that means partial u by partial t, it is partial phi by partial t plus partial psi by partial t. So instead of partial phi by partial t, we substitute c times partial phi by partial x. Instead of partial psi by partial t, we substitute minus c partial psi by partial x, and we equate that to g of x. Okay? Then we divide the two sides of this equation by c. That means partial phi by partial x of x minus partial psi by partial x of x equal 1 over c times g of x. So to obtain, if we integrate the two sides of this later equation here, okay, we obtain phi of x minus psi of x equal 1 over c times the integration from 0 to x g of s ds. And this is the second equation we obtain from the second initial condition, this initial condition. Now looking at the two equations 5 and 6, we see that if we add the two equations, we will obtain 2 phi equal f plus 1 over c integration g from 0 to x. That means phi is half f plus 1 over tc times the integration of t with respect to x. And similarly, we can find a formula for psi in terms of the function f and this term here. So we get psi equal phi equal half f of x plus 1 over c integration g of s ds from 0 to x, and psi equal half f of x minus 1 over c integration g of s ds from 0 to x. Now instead of x, we substitute x plus ct for phi, and we substitute x minus ct for psi. Okay, that means phi of x plus ct equal half f of x plus ct plus 1 over c times integration g of s ds from 0 to x plus ct. Okay, and psi of x minus ct, the same. Okay, we obtain this formula here. But actually we are encountering two problems with these definitions of the functions phi and psi. The problem that encounter the definitions of psi and phi are that the functions f and g are defined only inside the interval from 0 to L. That means x minus ct, if x minus ct is less than 0, which means x is less than ct, then we cannot evaluate the function psi. Also, if x plus ct is bigger than L, which happens when x is bigger than L minus ct, then in this case we cannot evaluate the function phi. So the solution for this problem is to extend the definitions of the functions f and g to include the interval from minus L to L, and then to make this extension a periodic function through the whole real line with periods to L. These extension functions shall be periodic, shall be defined in minus L to, interval from minus L to L, and periodic with periods to L. So we define the first function f of x to be capital F of x, uh, just f of x if x is in the interval from 0 to L, and minus f of minus x if x in the interval from minus L to 0. In a similar way, we define the function g of x. So through these definitions, f and g are odd extensions of the functions f and g. Yeah, here we still require that capital F and G are periodic functions. Now we redefine the two functions phi and psi by writing them in terms of the extended definitions of the functions f and g, so that 5x plus ct equal half this formula, and if psi of x minus ct equal this formula. We see that now the functions phi and psi are defined for all the values of x and t. Okay, any real number x and any positive real number t. Finally, the solution function u of x and t can be written as 5x plus ct plus psi of x minus ct. Then when we add these functions together, we obtain half f of x plus ct plus f of x minus ct, which is this first term. And when we add these two terms together, we obtain this term. And then that is the D'Alembert solution for the wave equation. Okay. Finally, we shall verify that the function u of x and t fulfills the boundary conditions. So we try to see whether u of 0 and t and u of L and t are zeros. We start with substituting x equals 0 in the form of the function u. So we obtain f of 0 plus ct plus f of 0 minus ct over 2. And here when we replace x by 0, we obtain this integration. Let us evaluate this function here, which is f of minus ct. And since f is an odd extension of the function f, then this function is just minus f of ct. Okay, that means we are adding the positive to a negative value, and then we obtain 0 in this term here. Also, we have g of s is an odd function in the interval from negative L to positive L. So that means its integration from minus ct to plus ct is 0. So that proves that the first boundary condition, Dirichlet boundary condition, is fulfilled. Now we go to the second boundary condition, where we replace any x with L, so u of L and t equal. So now we have this formula here. Okay, again we see that since f is periodic with period 2L, then we can replace this argument here, L minus ct, by L minus ct minus 2L, because when we subtract 2L or add 2L, then we are at the same point, okay, at the same value for the function f. So when we subtract 2L from here, we obtain f of minus L minus ct. We can take the minus as common factor here, and we take it outside because it is an odd function. Then this term vanishes. Okay. Similarly, this term vanishes. Okay, because yeah, we are integrating from negative L plus ct to positive L plus ct, and that is 0. Actually, that means the boundary conditions, the homogeneous Dirichlet boundary conditions, are fulfilled by the formula of u of xt given by the D'Alembert solution. In this slide is just like explanation of why this integral equal to 0. Okay, so just go through it if you could not understood it from the previous slide. Now we consider this example to clarify the idea of the D'Alembert solution. So using the D'Alembert method to solve the wave equation described by equations 1 to 4 for L equal 1 and u of xt equal f of x equal sine pi x for x is 0 and 1, and ut of x 0 equal g of x equal 0. So g of x is 0. Now to solve this problem, we first look for extensions for the definitions of the functions f and g. And since g is the 0 function, we just keep it 0 in the interval from -1 to 1. And since the sine function is an odd function, then we keep f of x equal to sine pi x, but we extend this definition to the interval from -1 to 1. Now the solution u of x and t, since d is 0, the integrand part of the formula of the D'Alembert solution formula is 0. So we remain with only the part that contains the function capital F. Okay. So then u of xt is given by this function, which is sine pi times x plus ct minus sine pi times x minus ct over 2. We know that we can use the expansion of sine, the sum of two angles, here the sine of the difference of two angles, and then when we simplify, we obtain this solution, sine pi x cosine pi ct. This is for the function u of x and t. We can verify that this function fulfills the differential equation, the initial conditions, and the boundary conditions also. For example, if we wish to check that it fulfills the boundary conditions, we see that u of 0 and t, that means we substitute x by 0, which is sine 0, which is 0, and then multiplied by cosine pi ct, that is 0. So it is 0. Also, u of 1 and t equal sine pi cosine pi ct. And sine pi is 0 multiplied by cosine pi t, that is 0. So it fulfills the boundary conditions. The D'Alembert solution can be extended for infinite domain. So if we have, the wave equation for x defined over the whole real line and for t bigger than 0 with initial conditions u of x and 0 equal f of x for x between -infinity and +infinity, and also partial u by partial t of x and 0 equal g of x for any real number x. And then we again keep the homogeneous Dirichlet boundary conditions, limit u of x and t equals 0 as x tends to positive or negative infinity. Okay. Now the solution of this problem, okay, is just obtained by following similar step to the step that we followed to compute the problem, the original problem, in 0L, and we end with this solution here. Since the functions f and g are defined for all values of x in the real line, then there is no need to find extensions for the definitions of f and d. So we can use f and g that are given by in the initial conditions. So this becomes the solution of the when the D'Alembert solution of the wave equation in the infinite domain. In this example, we using the D'Alembert method, solve the wave equation described by equations 7 to 10 for c equal 1, u of x and 0 equal f of x equals 0, and u of t, ut of x and 0 equal g of x equal 4x divided by 1 plus x squared. To solve this problem, now we see that since f is 0, then u of x and t is just of the form 1 over 2c times integration g of s ds from x minus ct to x plus ct. Now when we substitute c by 1, here we obtain half, here we obtain x minus t, here we obtain x plus t. And when we substitute g of s, by the value of g, we obtain 4s divided by 1 plus s squared. And this integration equal ln 1 plus s squared with the boundaries of the integral or the limits of the integral x minus ct and x plus ct. So when we substitute x plus ct, we obtain ln 1 plus x plus t squared. And when we substitute x minus ct, we obtain ln 1 plus x minus t squared. But we know that ln minus ln is ln the ratio between the two. So this becomes the final, the solution of the given wave equation. Thank you so much for attending this lecture. I'm hopeful to see you in the next lecture, which will be about solving the wave equation using the Laplace transformation. Thank you.